For scientists, the questions were immediate and endless. Why was this object so large? What could its chemistry reveal? And what surprises might unfold as it raced closer to the Sun? At a distance of about 2 astronomical units, roughly 300 million kilometers from the Sun, 3I/Atlas is already breaking the rules of solar system traffic. Its course is no lazy arc. The object is barreling along a hyperbolic path, a trajectory so steep that not even the Sun's gravity can pull it back. Right now, the comet is moving at nearly 60 kilometers per second. That's more than twice the speed of any planet in orbit, and fast enough to cross from Earth to the Moon in just over an hour. For comparison, Earth's own orbital velocity is a modest 30 kilometers per second, and even Mercury, the fleetest planet, can't keep up. This isn't a gentle cruise through the inner solar system. As it approaches perihelion at the end of October, 3I/Atlas is still picking up speed, projected to hit nearly 68 kilometers per second. At that pace, the comet's journey is a true sprint, one that will carry it past the Sun and out into interstellar space, never to return. The laws of orbital mechanics dictate that only visitors from beyond can achieve such a hyperbolic escape. Most comets and asteroids are bound to the Sun, looping endlessly in ellipses. 3I/Atlas, by contrast, is on a one-way trip, its path a straight shot from the direction of Sagittarius. The sheer velocity of this object is more than a numerical curiosity. It means that every observation is fleeting, every data point precious. Astronomers know they have only a short window to catch this traveler before it slips away. Each night, the comet covers millions of kilometers, changing position against the background stars at a rate that strains even the fastest tracking systems. The pace is relentless, and the opportunity is rare, a cosmic sprint that leaves little time for second chances. In early September, a quiet tension swept through observatories worldwide. Photometric charts from Hawaii to the Canary Islands began to show the same jarring pattern. 3I/Atlas was brightening at a pace no one had forecast. On September 10th, its apparent magnitude hovered near 15.5, a faint smudge for most telescopes. By September 17th, that number had leapt to 14.2. Just a week later, the comet's brightness had rocketed to magnitude 12. The flux had increased by a factor of 6 in barely 2 weeks, a rate so steep that seasoned comet trackers double-checked their calibrations, suspecting software glitches or atmospheric haze. Every check only confirmed the numbers. The light curve, plotted night after night, didn't just rise, it shot upward in a near vertical spike. As the data poured in, the scale of the outburst became clear. The coma, once a modest envelope, had ballooned to over 85,000 kilometers in diameter by September 24th. That's a cloud of dust and gas, sprawling wider than many planets, with some estimates putting its cross-section on par with Jupiter. The expansion rate itself was staggering, nearly 4,000 kilometers per day, as if the comet was detonating layer after layer of ancient ice and dust into space. Each new measurement forced astronomers to rethink their models. Was this a deep internal pocket of volatile ices finally exposed to sunlight? A slow-motion surface fracture, or a sign of more violent fragmentation hidden beneath the coma's glare? No one could say for certain. The suddenness of the surge set off a chain reaction among global astronomy teams. Emergency teleconferences linked research centers in the US, Europe, and in Asia, with scientists debating the possible triggers late into the night. Some pointed to the timing, just as the comet crossed the critical threshold for subsurface ice crystallization. Others wondered about the role of solar wind, or even the possibility of a recent impact. With the comet racing toward the Sun and Earth's viewing window shrinking each day, the scramble to gather every scrap of data became urgent. For astronomers, it was a rare, fleeting crisis, one that demanded answers before the comet slipped behind the Sun and out of sight. By mid-October, a new threat loomed over the global campaign to study 3.9/Atlas. The comet's relentless plunge toward the sun was closing Earth's window of opportunity. Each evening, the object dipped lower and lower, its path pressed into the thickening twilight. Astronomers watched as the solar elongation, the angular distance between the comet and the sun, shrunk day by day. Once that angle dropped below 30 degrees, scheduled for October 21st, the rules of ground-based astronomy changed. Telescopes, no matter how powerful, faced a hard limit. Pointing too close to the sun risks blinding sensitive detectors or damaging mirrors. Professional observatories began to withdraw, their tracking files replaced with cautionary notes and blackout dates. For a few desperate nights, only the most determined observers, armed with special filters and a willingness to chase the comet at the horizon, could capture fleeting glimpses. The practical viewing window narrowed to a razor's edge, just after sunset or before dawn, with the object barely clearing rooftops before vanishing into the sun's glare. Even then, atmospheric distortion and city lights made each measurement a gamble. Data streams that had once been steady now stuttered and faded. By October 21st, Earth's direct line of sight collapsed completely. The scientific world braced for a total blackout. No new images, no spectra, no brightness updates. Every unanswered question about the comet's outburst and chemistry would hang in suspense. With the sun now blocking Earth's view, the burden of observation shifted elsewhere. The countdown to Mars flyby began, and the urgency to make sense of this interstellar visitor reached its peak. Mars orbiters became the new front line as 3I/Atlas swept toward its closest approach, just 28 million kilometers from the red planet. Inside mission control rooms across 3 continents, planners worked around the clock, recalculating trajectories and updating tracking files. Every adjustment mattered. The comet's speed and unpredictable brightness demanded simulations that ran for days, not hours, each one refining the pointing commands for cameras and spectrometers. On Mars Express, engineers rewrote observation scripts to fit the comet's shifting path, squeezing in imaging runs between long-standing science commitments. ExoMars Trace Gas Orbiter's science team lobbied for extra time, hoping to catch rare gases in the coma just as the surge peaked. Meanwhile, NASA's MAVEN team prepared its ultraviolet spectrograph and plasma instruments to monitor the shock front as solar winds slammed into the expanding cloud of dust and gas. The high-rise camera on Mars Reconnaissance Orbiter, famous for its sharp views of Martian landscapes, was repurposed for a different challenge, attempting to resolve the comet's nucleus from millions of kilometers away. This required not just updated ephemerides, but also real-time coordination with ground stations on Earth. Negotiations over data bandwidth and observation slots grew tense. With only a narrow window as 3I/Atlas swept past Mars, every instrument team argued for a piece of the action. In the end, a time-sharing plan emerged, ESA and NASA splitting the critical hours, with Russian teams pressing for a last-minute extension. For the first time, the science of an interstellar visitor would hinge on a relay of robotic eyes circling another planet, ready to capture whatever secrets the comet revealed as it barreled through the Martian sky.